All right, I've got one more equivalent force system example. Let's work through. So we've got this kind of a U-shaped structure that's upside down with a handful of forces applied to it. And they're gonna, you got point A down here. You've got a distance of 1 meter. And then we're going to have, so halfway up, so this is vertically 1 meter, so it's horizontally 1 meter. Vertically, it's going to be 1 meter. I've got half a meter here. And at half a meter, I've got a 20 Newton force in the positive x direction. It's another half meter up to the top. Again, this thing's 1 meter tall. At the very top, right up here at the very top, I've got a force. We'll say that this is 50 newtons. And this is described by a similar triangle. 3 in the vertical, 4 in the horizontal. It's a 3, 4, 5 triangle. 3 in the vertical, 4 in the horizontal. They put a couple moment of 100 Newton meters right here in the middle of this thing. And then over here at the far edge, just to make the math awkward, they put this 30 Newton force at an angle of 45 degrees from vertical, and that is a height of 0.7 meters. This thing was actually going to be pretty easy to do mathematically until we added that. Now I apologize. I thought I'd put that on silent. Okay. My phone. Okay. So what are we trying to do here? We're going to replace the system of loads. Loads can be forces, couple moments, or later we'll talk about distributed loads. We're going to replace the system of loads with a single force and couple moment at point A. So we mentioned last time, a very simple way to do this mathematically is to just go through and find the resultant force, or the sum of forces. So I'm going to find the resultant force in the x direction, and then we'll do the same thing in the y direction. So in the x direction, I've got 20 newtons. Also in the positive x direction, I've got part of this 50 Newton force. Now, the 4 is horizontal, so basically I'm looking for the sine of this angle up here at the top. The sine of this angle will be the 4 over the hypotenuse 5. So it's going to be plus 4/5 of that 50 Newton force. Again, the 4 is the horizontal component. The hypotenuse is going to be 5, so it's 4/5 of that 50 Newton force. And then in the negative x direction, I'm going to have part of this 30 Newton force. Now, if it helps, feel free to draw this thing resolved, with all the forces resolved. If you're comfortable just working from this and resolving as you go for it. If you need to draw this resolved, please do. I'll show it to you here. If you want to do it, pause, go ahead and draw yours resolved if that's what you're wanting to do. I'll show you what the answers look like here. Here it goes. So this is what it would look like resolved with numbers. You can pause it there if you like. Okay. But we'll just work this one unresolved, and we can just resolve it on the fly, so to speak. So this is the x component of this 30 Newton force is in the negative x direction. It's pushing to the left. That is going to be opposite of that 45 degrees. So it's minus 30 newtons times the sine of 45 degrees. Now with the 45, you can kind of cheat a little bit. It doesn't matter whether it's sine or cosine. I have written here that if I run these all out through a calculator, I find that to be 38.8 newtons. And then if I do sum of forces in the y direction, that's going in the up direction. I've got that 30 newtons, only part of it is the cosine is the adjacent because the vertical is the adjacent side here. So it's going to be the cosine of 45 degrees. Again, numerically it doesn't matter on a 45 degree whether it's sine or cosine, but you will encounter plenty of angles where it's not 45. So be comfortable figuring out, oh, is that sine or cosine? You really want to make sure you know how to do that. On this force has a negative y component. The vertical component here is the 3. So that means, and again, it's down, so it's negative. And since the 3 is the vertical, it's going to be 3/5 of that 50 Newton force, which is a minus 30 newtons there is what that equates to. Run this through your calculator. Pause here if you want to get an answer and then double check it. Okay, so I've got here a minus 8.8 newtons. That's what I found that to be. Okay, and then sum of moments, and again, we're trying to move everything to point A, so I would take the sum of moments about point A. Now notice these forces don't have distances. Forces don't have distances. Moments have force times distance. So I don't really care where the forces are located here. They're on the object somewhere, so they've got to be added. But the moments, the location of those forces is critical with the moments. So we're gonna have to do that. Okay, so from point A, we're gonna have several terms here. I've got 20 newtons from point A. It is causing a clockwise rotation. Again, put your pen there, push in the direction of that 20 newtons. Notice that is trying to push in a clockwise rotation. So it's a negative moment. 20 newtons at a distance of 0.5 meters. It doesn't matter necessarily the sign or the direction. Is it causing clockwise or counterclockwise? Because again, we're saying that counterclockwise is positive. So this is a clockwise moment, minus 20 newtons times the 0.5 meters from point A to the line of action for that force. And then we've got two components up here, right? Two components. Notice the vertical component is going right straight through A. So the vertical component, you can write it out here. Let's just kind of be thorough and let's look at the vertical component, the 3/5 of that 50 newtons. And notice that the distance is 0 because it passes right through point A. But the X component, this guy, that is a distance of 1 meter from point A. And it's trying to cause, again, this Y component here is trying to push this paper in a clockwise rotation. So it's going to be negative. The X component, the 4 is the horizontal, so it's 4/5 of that 50 newtons, and that's at a distance of 1 meter. I have a counterclockwise 100 newton meters. It doesn't matter where the moment is located. It's just a moment term that needs to be added or subtracted into our equation. And again, because it's counterclockwise we're calling positive because that's actually pointed up in the positive z direction out of the page at us. So that's plus 100 newton meters. And then I've got two components out here, right? I've got a vertical component going straight up. So I'm going to write it on the second line of this equation down here. Plus, I've got the 30 newtons, and this is going to be the cosine of that 45 degrees because the vertical component is adjacent to that 45 degrees. And it is trying to push this paper in a counterclockwise fashion, in a positive fashion. So it's a positive term, 30 newtons, cosine 45, and it is out at a distance of 1 meter to this vertical component. 1 meter to this vertical component to point A. And then the horizontal, the X component, is pushing this way, right? It's pushing in the negative X direction. Now, so the tendency might be, well, does that mean it's a negative moment? No. Look at the direction that this X direction force is trying to rotate. That X direction force is trying to cause a counterclockwise rotation. So it is also a positive moment. Even though it's negative X, it doesn't matter. It's a positive because it's trying to cause counterclockwise rotation. A positive moment of 30 newtons. The horizontal component is opposite of that 45-degree angle. So that is a sine 45 degrees. And its distance to the line of action for that horizontal component is this 0.7 meters from point A. All right, I'll pause there and let you get an answer. All right, you got it for me? So the resultant moment, the sum, when you add up all the moments about point A, the resultant moment ends up being about 86.04 Newton meters. And we've already seen the resultant force has a positive X and a negative Y component. So the resultant force, of the net force, ends up being 38.8 I minus 8.8 J newtons. And if you want to do this graphically, you just draw your structure. You apply force at point A, so it's positive X, negative Y, so it's going to go mostly in the positive X direction, a little bit in the negative Y. 38.8 I minus 8.8 J newtons. You could find this, you could use trig and find the magnitude and the angle measured counterclockwise from positive X if you want. We talked about that early on in chapter 2. I didn't specify. This would actually be my preference as X and Y components of that force, honestly. And then we found that the net moment, when we added up all the moments caused to this thing, the net moment ends up being, or the resultant moment ends up being a positive, so counterclockwise, 86.0 Newton meters. Would I count you wrong for 86.04? No. If you gave me 86.047235, however many digits, I probably will count you wrong for more than 4 significant figures. I probably won't count you wrong for 4, but try to keep it at 3 significant figures. Okay? All right. That is probably enough lecture here. I am going to show you, I mentioned earlier, we had this other example, another 3D example of a moment problem. This guy, if you want to set this up and then kind of work through, I'll show you the solution. But basically, this is like a ratchet or a wrench where you've got something at the origin you're trying to turn, and we're trying to push with this P force in the negative Y direction, so we're pushing back this way. 16 pounds, and the negative Y direction is the force, and you've got 0.75 inches as the head of this wrench, and then you've got a 10-inch handle that is at this weird 60 degrees from vertical. So basically this wrench is in the XZ plane. Right, so this wrench is in the XZ plane, and the force is in the negative Y direction. And then it just wants you to find what is the moment about the Z-axis. What is the component of the moment vector in the Z direction? And why that's important is because if this is a wrench and I'm out here trying to push on this thing to try to get it to turn right there, I want to know how much moment, how much torque I'm actually generating to cause this thing to turn. That's what you're trying to measure here. Is how likely is if there's some nut or a bolt head, how likely am I to turn it? And that's what they're asking for. Is what is the moment in the Z direction? So pause here if you want to work through it, and then I'll show you the solution real quick. All right, so here's how I saw it. Again, this wrench handle is in the XZ plane. It comes a 0.75 in the negative X direction, and then it comes up at an angle in the negative X and positive Z direction. So 10 inches at this angle, it's 60 degrees from Z or 30 degrees from X. So the Z component here is 10 sine 30. The X component, you come, again, from the origin, you're 0.75 inches before this handle starts, and then it's 10 cosine 30 to get out to the edge. So your position vector ends up, you've got an X component of minus this guy, the 0.75 plus the 10 cosine 30. It's in the XZ plane, so there's no Y component. And then this is your Z component. So this is your position vector that's going to get crossed with this force vector. So your moment is going to be the determinant of this matrix. So Rx, Ry, Rz, Fx, Fy, Fz. You do this, you do the determinant of the matrix. And again, the problem's asking for the moment in the z-axis. And so when you multiply that through, you find, well, it's actually 80 pound-inches being rotated about the x-axis, which is not the way you want to go with this. But you are getting 151 pound-inches around the z-axis to get this thing to turn. So you're kind of pushing at this angle. Not the good way to do a wrench, but you're still getting a good amount of torque in that z-axis. All right, that's a good stopping place. Hopefully that helps. I think that wraps us up in chapter 4. If not, we're very close.